Right, so thanks for coming along to me when there's someone who knows what they're doing in the other hall. This is about a talk on a project I've been working on and off for about a year now, on looking at live analysis of volatile memory. By that I mean RAM, rather than staking forensic dumps of it. Compulsory who is, I'm a third year ethical hacking student here at Securi-Tay. My main interests lie around where cyberspace meets the real world, so this is a bit of deviation from that. By that I mean like power plants, transport systems, sort of control units, but it's difficult to experiment with them at uni. I'm keen, but I would consider myself an amateur programmer. Just an introduction to this talk. It'll be fairly sort of high-level overview, looking at basics of memory. I imagine most people in here are familiar with them, but just a quick overview to bring people up to the level. A look at some data structures you can find in memory. So what are the artifacts we'll be looking for to get anything out of this project? Then a look at volatility and recall, which are the two main tools for static analysis, and we're looking at how we can use them for live analysis. And then finally, how we can customize the whole thing with Python. To start with, just have a look at memory forensics. So imagine, at some level at least, you're familiar with the idea of address mapping. The operating system and programs see virtual address spaces. They don't see the actual underlying RAM. The processor handles at the lowest level converting these address spaces into physical and vice versa. So when the operating system requests an address, it is sent to the processor, and then the memory management unit, or MMU, looks it up in a table and carries out the conversion. I won't go into the maths of the conversion at the moment, but it's not that complicated really. The MMU contains a buffer called the translation look-aside buffer, which stores a basic table for the lookup. There are multiple others, but that's sort of the first stage that it goes to find other tables and so on to look at. The diagram at the bottom there, don't know if you can see it on the right, is just a basic mock-up of how you would convert your virtual address into where it actually is in memory. So you have, in 32-bit systems, you have 32 bits of an address. The first 10 are your directory table. So it takes that, looks up in this table where that section is. Then that value takes you to the next page table, because there'll be multiple page tables. And then the next 10 tells you the offset within that table to go to, and then that to the next stage where you have the actual physical address. Now paging splits down your memory into sections which can be switched in and out of memory by the processor to make it more efficient, and also to allow a program to work as though it had access to the entire 4 gigabytes or however much RAM you have in a machine. It doesn't have to pay any attention to how much other processors are using. The processor will just switch stuff in and out as it can. This 32-bit supports up to 4 gigabytes of RAM, but there's also a mode called physical address extension, which sort of changes this system, adds a couple of stages into this system, which supports up to 64 gigabytes of memory. And 64-bit, it's basically the same theory. At the moment, I think I'm still correct in saying that no processors use all 64 bits. Most of them, Windows 8 certainly, uses 48 bits of the address. The remaining bits are set depending on what the last bit of bit 47 is set to. If it's a 1, then the rest of them are 1s. If it's a 0, the rest of them are zeros. The page sizes are slightly different. You have 4 kilobytes, 2 meg, or 1 gig. And these are dictated by flags set within the address, the actual address value. Just to have a quick look at this again, say there page map and directory pointers added to the other tables. So basically what I mean there is that there are 2 more stages at the far end there, which give more memory size. Actually, just point out quickly, this CR3 here, that is a register on the processor, which stores the base of the lookup tables. So that is the first stage that's always injected to tell the processor where it should start off looking for the look-aside buffer, basically. Just moving on from that, we have privilege levels. Again, I imagine most people are familiar with this, so just quickly to go over it. You have most processors will, and it's different for Windows and Linux and I presume Mac, although I know very little about Mac, will follow something like this. So ring 3 is where any programs we use run, PowerPoint or whatever. Any of those run within ring 3. Ring 2 and 1 are mostly used by device drivers. So things like your graphics card driver, your sound card, that kind of thing. Ring 0 is the kernel. So that's where sections of the operating system will run with maximum privilege to access any part of the physical hardware without any kind of restrictions placed on them. Obviously, this is designed so that things running in ring 3 or user programs can't be written to just access any section of memory, alter other processors' memory. It's a protection thing to lock down what's available to them. So these you get from ring 3 to ring 0 by using system calls. They're generally called IOCTL or IOCTL commands. And this allows you to make calls down to the Windows, in this case, Windows kernel, to say read a file, access memory, open up, access a graphics card, that kind of thing. So you can't write code that does that itself. You have to use the existing API built into the Windows kernel. So this is a quick summary. User mode programs are presented a range of virtualized addresses. They cannot access any address outside this range and are not aware of the physical addresses to which they're mapped. Obviously, that fact that they cannot access any addresses can make live analysis quite tricky because you can't write a program at the basic level to just read any memory. This is just more quick summary. I won't come back to this afterwards. The OS implements two kinds of protection on memory. DEP doesn't actually affect this process at all. We're not trying to get anything to run where it shouldn't. And DEP simply marks certain areas of a binary as non-executable. So that's not a problem for us. ASLR is more of an issue, because it makes it very hard to find what links to what within memory. Instead of having a nice compact binary, you've got stuff spread over a much larger area. So if you're doing it from scratch, that's a much more difficult thing to overcome. Not impossible, but difficult. So now I just want to have a look at some of the data structures that are interesting to us. The main one I'm going to be looking at today for time's sake is our processors. Now within memory, these are defined by the eProcess structure. I'm not sure if you can see that all right, but this is basically how a process is in memory. This, not layout-wise, but what it has. So you'll have the eProcess, which contains all the information about it. You have threads, can be any number of threads, conceivably. You have a handle table to any file objects and so on that it has open or needs to open, any memory call, system calls, that kind of thing. You have SIDs for who runs it, what level of privilege do they have on the machine, and what access does it have to the machine. Loaded modules are basically your exe. So if you look at this within memory for, say, notepad.exe, you would have this eProcess which defines everything, but then within the modules you would have the actual string to where the exe is on your on your hard drive, in your file system. The VADs are virtual address descriptors, and they describe all the various address spaces which are allocated to this process. Now, each process is doubly linked to other processes. So what that means is you have, within the structure, this active process links object. And that contains two fields, flink and blink, which is just simply forward link and backlink. And they relate to a tree of a line of processes. So every single one in memory, theoretically, is linked to this string by having a link to the next one in line and a link to the previous one in line. that link starts in kernel debugging memory, where there is an address which starts that process, basically, a string which starts that off. Things like Task Manager, I believe Process Explorer, the third-party tool, they rely on this list to show you processes. So they walk through this list and list all the data that they pull out of that. That is not 100% foolproof, because it is possible. None of the values within the eProcess header are actually critical to running a process. So it's possible to alter these lists to basically unlink it and leave it hidden within memory, so not visible to things like Task Manager and so on. So that's an alternative to trying to name it something different. Now you can use the Windows debugger to have a quick look at the structure. I've cut out quite a lot of it because it would have gone on pages otherwise, but just kept in some of the key ones. The PCB is the process control block that contains critical fields, including things like the time spent in memory, the time that's been paged out of memory, and the amount of time it's spent in kernel or user mode. Create exit time, they're just UTC timestamps telling you when the process was created. The exit one will be 0 until it is actually exited. The unique process ID is your PID, the thing you would see in Task Manager. And you can see there the active process links is the doubly linked list telling you which is ahead and which is behind it. Session process links is very similar to active process links, but relates to the session on the computer. So this would be the for user, perhaps, most likely, where all the processes one user is running would be linked separately to the normal active process links field. Token is your security token defining the SIDs. Inherited from unique process ID is the parent PID. The PEB is the process environment block, which contains some of the addresses, a listing of addresses and so on that you have available to this process. The ones fairly self-explanatory: active threads, or the number of threads available running under this process. Your thread list head is a pointer to the e-thread structures, which define threads within a process. And image file name is the first 16 characters in ASCII of the path to the image, so your .exe. So how do we identify processes within memory? It's, as I say, the basic way is using your kernel debugger data block and walking along the path of PS active process head lists. Now, as I say, that is not 100% foolproof if you're trying to do an investigation into a machine rather than simply see what's running on your machine in an ideal environment. If you're interested to see if something malicious is being done, that doesn't necessarily show everything running on the machine. And so Recall's PS list plugin relies mostly on this, as do process list and task manager. Another way is to literally just scan through the memory pool for any eProcess objects, which you can find through looking for signatures based on the structure we saw. That, again, is more foolproof, but does often, from what I experimented with, does often cause false positives, because a lot of things can look very similar. It seemed to throw up a lot of eThread objects, for instance, as well, when I was using Recall for that. Then there are alternate process listings, which work in very much the same way as the active process head thing. You've got thread scanning, where you can look for, instead of eProcess blocks, you look for eThread blocks, and you can assume that they will be linked to a process. You can then work back up to see what their parent process is and map processes this way. This client-server runtime subsystem is involved in creating and killing every single process, regardless of whether you've hidden it or not. So again, that maintains its own handle table, separate to everything else, of all processes running on the machine, and also threads. That, again, it's possible to get into memory and edit that to remove threads, but you're adding more layers of difficulty here. The final one is PSP CID. This is a special handle table within kernel debugging memory. Again, it's slightly redundant, but it's just another way of checking. It stores references to all active processes and thread objects, but only active ones. As mentioned at the bottom there, a couple of rootkit detection tools called Blacklight and Ice Sword use this method, but it was proved academically to not be foolproof, and that you can still edit that table to remove processes from it and hide them again if you want. Just put at the bottom here, it's not very easy to read, but this is me running recall, the PS list plugin on recall just to list processes, and you can see maybe the different methods it can use here. So you've got PS active process head, CSRSS, PS PCID table sessions and handles. So you can see that each of those can be used for that. Just a quick look at some other structures. To say I'm mostly focusing on the processes today. You've got your standard C, C++ data types, your strings, your integers, your lists, your trees. Singly and doubly linked lists, your standard arrays, almost all doubly linked ones with your F-link and B-linked values. And trees. Linked lists and trees are very hard to detect on their own in memory, because you don't know really what is linked to what. The doubly linked lists are a little bit easier because you can find B-linked and F-linked values, but singly linked lists and trees are quite hard to locate. Then there are other OS-related structures like eProcess, which include eThread. Now you can find a summary of those through WinDebug by actually running that command with a star at the end, and that'll list all of them, and then you can refine it down. If you just entered thread where the name is, then it would list all kinds of thread objects, eThread, pthread, multiple different kinds of thread objects, which you can then go into in more detail and get listings like I had quickly processed earlier. And these just consist of a number of standard data types. I'll have a look at volatility and recall, what are the main tools I've been using besides Python. Just a quick summary of them. Volatility was first released at Black Hat DC in 2007 and was sort of adopted as the best around as far as I can tell. It's very comprehensive and built on years and years of academic research by the authors. I think there's 4 or 5 of the main authors. And these people have now more recently published a book called The Art of Memory Forensics, which, if this is something you're interested in, I would recommend. It's quite a heavy read, but it's excellent. In December 2011, they created the Cadet branch, which was intended to increase modularity, increase efficiency, and make it just more usable rather than being a pure out-and-out command line tool. After a couple of years, this hadn't been adopted into volatility, and the creators of Recall of Cadet got destroyed, so they split off themselves and became Recall, a completely independent project. It includes slightly more external contributions than volatility, which is very much a work of the 5 core people with plugins written by some community members. Recall does its memory capture using a third-party tool, and a lot of its code base has been edited by community sources. Personally, I found it slightly more usable than volatility, as I suppose it was intended to be, and also a little bit more powerful. It seems to be updated faster for new operating systems, which was useful at the time to switch to Windows 10. So if you're using these for static analysis, you can acquire an image file with just a simple command like that. Recall AFF4 acquire. This uses their own custom memory forensics capture file. They created the AFF4 format to replace things like more .elf and crash dumps in the Windows, because they saw issues with those if they're trying to write a fast, usable tool. They have no ability to store sparse regions of memory, so all reserved regions are padded out with zeros, which gives a larger image size than strictly necessary. So if you have a direct memory access, a card which requires direct memory access, say a graphics card, then it might reserve a certain amount of RAM, which would then just be a block of zeros, which are completely meaningless to you. So it doesn't allow you to crush that down. The other ones also had no support for compression or encryption, which they felt were very valuable things because capturing memory is slow. So by using compression, they're able to speed up that process somewhat. Yeah, I think recall can capture at 250 megabytes a second. So it doesn't take long to take it. This has 2 gigs of RAM, and it takes no time at all to image the whole thing. There's also no support for additional metadata, which was something they wanted. They wanted to not have to do a complete fresh start scan every time you were looking at an image. So when it takes the image, it's also pulling out certain fields and storing them with the image to make the whole process of analysis a little bit easier. And they also wanted to include things like the page file, kernel header, and so on. This is just an example of running PS list on their file. Looks very standard. You can see down the left, those are the virtual memories, virtual memory addresses. You can also set it to show the physical memory addresses if you want to. So if we want to run recall on a live system, we need to introduce another step. Well, technically we don't, but I'll go through it the longer way first. WinPMem, or the PMem acquisition suite, was created by another person, I get them confused with the authors of Volatility. It comes in a .exe, or you can get the C code files, or there's a Python library for it. It basically contains 2 drivers for x86 and x64, which run at kernel level. So they handle the actual gathering of the memory. I forgot to put it on the slides, but they also have functionality to enable write mode, so that you can write arbitrarily to memory, which is quite interesting, because you'd be able to use that to, say, hide your processes if you wanted to, edit the header files, edit the tables, and so on. So it's included as part of Recall, and is now maintained mostly by Recall, or the Recall Foundation, but is also available as a standalone thing. If you want to use it in Python, you literally just import it as anything else. I couldn't be bothered finding out the exact module, so I just imported it. Yeah, so it includes the assigned kernel mode driver. If you run it here, you can see the name of the driver in here. It's a bit fuzzy, so I'm just running the Python file here with the D tag to tell it where the driver is, and then the -L to tell it to load the driver, but then not do anything with it. It just loads the driver and shuts down. So you can see here the address for the CR3 register, the kernel space addresses, the physical addresses, and then your virtual memory ranges down here, which you can interact with. Just a little summary as you go, as you fire it up. It also creates a file handle. So it loads the driver and then creates a handle to them, which is the //./pmem. Now this acts as any other file. You can open it using C++, just create file. It's just a file handle. So you can attach recall to it as though you're attaching it to your .aff4 capture file. So that's me running PS list live on the machine without having taken a capture file beforehand. Yeah, there is an option in recall which is just --live, which can replace the file name there. It does exactly the same thing. It just loads the driver for you and just gets your step basically. So if we want to look at customizing it with Python. So recall has a Python library to pull from. It has heavy support for writing plugins, writing parsers if you wanted to look for certain data structures within memory that they don't have support for currently. It has support for writing things with different image files, because obviously they rely heavily on AFF4. It does support RAW and the older formats, but if you for some reason go for the new one, you'd be able to write a plugin for it. You can also just use it to automate it, which is what I'm most interested in here. To try and use it as an automated detection tool rather than a static memory, a static analyzer for after the events happened. I want to detect things with it instead. So your basic session, that just creates an instance of recall. if you're using if you're using it live, you just replace this with your .pmem address, and then the URL. Recall and volatility require a profile for the operating system you're working on. So they need to know where to look for things, how to read things. So they have profiles for each operating system, and each version of operating system you'll have service pack versions as well. Normally, Recall handles that very well and automatically detects which one you're running, much better than volatility does. And so you just feed it that URL and it'll look up the correct profile for you. And then just use print, and you can output any plugin value. So yeah, I think I mentioned this before, but yeah, yes, you'll be able to write support for image format. You can also do output renderers if you wanted to format it into a special file, your JSON, XML, and so on, to view it in a particular way. So you can also skip the recall step altogether if you want to script things and just use WinPmem, which also has Python libraries, and you can load the driver and just interact with it as though it was a file. It's a lot more complicated because you're just reading raw memory. You haven't got any of the assistance that's been built into volatility and then recall, which has taken years of a team of people much better at this than I am. So you're starting from scratch again, but if it has a particular purpose for it, it might be the way you want to go. It runs on Python 2.7, as is every damn thing. You also need PyWin32, which is Windows extension for Python. So it enables you to do things that you'd normally do in C, C++, like you can create a file, to interact with things in a better way. You can't actually open the file as though you're doing it in Python if you're using Pman. Yeah. So just a basic, this is from my script, I've got just my basic read function. So I set the file pointer, read the file at the top, and that is literally it for reading from memory. The rest of it is just dumping it to a log file. So 2 lines, just as though you're reading a .txt file, .txt file, and you've read memory. You then have the problems of working out which memory you read. So volatility and recall handle address translation for you. So they handle translation from your virtual addresses to physical addresses. So if you can use them interchangeably, and you can just reference them, and it uses its code to work out what's connected to what. So to not use that, I was getting very confused by what I was getting. One of the biggest problems I was having, for instance, was it kept detecting my own program. So I would input search for notepad.exe, and 9 of the 13 results I might get would be variations on search string for notepad.exe. So that was one of the problems I was having originally, was working out what was actually meant to come back and what was coming back. But with a bit more time, I'm sure that can be got around. This outputs the data as a string, so it converts it to ASCII. But my latest version dumps it as hex instead, because it's a bit more useful, rather than just random ASCII characters if it's not actually a string. Dumping processes. This was something I was looking at more recently. You can use recall to dump processes. So if you were trying to analyze whether a binary had been changed, but you couldn't get hold of the original binary, you just found it in the running machine, you can use a plugin that's already written for recall to just pull that binary out. It's not immediately runnable, it's missing handle tables, and I'm not actually sure what else. I was looking at this last night. But it can fairly quickly be rebuilt to actually run click as normal. I want to try and do a quick demo of that just to show you how recall works. So if we go the long way around and just start off with WinP mem, hopefully I'm in the right directory. So there's the output from WinP mem, and I now have the file object which I can use on recall. So, I've just got a basic hello world program compiled with a no SLR option, no ASLR option to demonstrate. So there I'm just listing the processes, but I only want it to show the one that is matching hello world. I just need this to get the PID. I could do it through Task Manager, but that's boring. So now I've got the PID. So that's just telling it where to dump the exe to, and then the PID that I want to forward. Fingers crossed. Okay. So if I can just pull this up, you can see there the size 164 kilobytes, which is exactly the same as I'm hoping. As the original no ASLR.exe. So the only thing that's different is its handle table is broken. And I'd have to rebuild that manually, and then it would be able to handle system calls that needs to print to the screen and so on without crashing. But I'll pick up that at the moment. It attempts to run it. I should then pop up saying not working. Or not pop up at all. Oh yeah, it's not on my main screen, of course. It's just that. But that, as I say, you can rebuild it to actually run properly. You can also see from that that recall is fairly quick, even when using an unlive system. It pulled out the process, for instance, fairly fast, and that's using all of the methods, the defaults when you use PS list to every single one of the methods I mentioned earlier. So it's done that pretty quickly. Okay, my machine is not running a huge amount, but I'm sure I've got some junk on there that shouldn't be running. So my next steps for the project, obviously this has been more of an overview rather than a look at my actual, sort of where I've got to with this. And that is because I sort of went around in circles for months. So I have a Python script that reads memory, searches memory, and also to an extent monitors memory, so I can input an exe I want to look for, or just a wildcard value, so anything .exe, and it will go through, documenting the ones it finds and notify you of any new ones. So that was where I wanted to get to, but the false positives were too big to make it actually workable at the moment. But we'll get there. So my next steps are using recall instead of just going all the way down to WinPMM to try and monitor and flag up processes which shouldn't be there. So the basic example might be system processes which are being abused. Services.exe, for example, should always be running, but only one of them should be running. So but there's no checking that in the OS. So if you have something like this, it might be something which malware would try and hide as, so on. It's just an example, but there are other ones which are probably used as well. Doing my own program, say I have the issues with address mapping, ASLR becomes a problem, which volatility gets you round, and there are things like the issues I mentioned where you can't, it's very hard to work out what is a tree, what is a list, and what isn't. You get it's very complex to work out which ones are, which ones aren't, which are just false positives, which are just string variables. So it's quite a long job to get the Python program working. My ultimate ambition, and the main reason I actually started this project in the first place, is the Yara stage. I would like to have it running an automated detection on known malware in memory using Yara. Well, Yara being the easiest way of doing it. A lot of malware now to try and avoid antivirus, try and avoid other detection techniques, tries to maintain itself in RAM for as much of its lifetime as possible without leaving a footprint on the hard drive. So if we can use something like this, it might be a way to try and catch some of the known ones. Signature detection obviously only works on known malware, but it's somewhere to start. So that is the end of my talk. Thank you for listening. I don't know if these slides are going to be available online anywhere, but I stuck some references at the bottom there in case anyone's interested. A couple of books and a couple of links I used. And my GitHub at the bottom there has my current Python tool, which I need to update. I haven't updated in a while, but you can see roughly what I'm doing with that. So, thank you very much.